I am one of the founders of VBN Components, and we are very happy to be here and present our material knowledge for you. We also say welcome to all of you attendees here in the webinar. It's all about a new type of wear-resistant materials, and it's all of them are made by additive manufacturing. And who are we at the VBN Components? I will see, I can change. I'll try to switch here. It doesn't work. This is VBN Components. We are a materials developing company. We have been working in materials for many years. And this is based in, you can say it is from the Swedish powder manufacturing industry. And myself and fellows around here, we have also been much into tribology. That is the knowledge and the science of wear and friction of materials. So this and the powder manufacturing led to the idea of the additive manufacturing of these kind of materials. And now we've been active for more than 10 years. And here in Uppsala, we have an additive manufacturing production unit, which we produce and develop new materials. So the basis of the companies is materials, powders, additive manufacturing, 3D printing, and the tribology. This is the base of the company. We have, since we've been around for more than 10 years, we have won a lot of prizes. We are, of course, very proud of them. So you can just see shortly here about them. And latest, we've been nominated in the Best of Industry Award, which we also are very proud of. I will see how it comes up in the end up to this award later on. Our vision is to renew the materials industry in the world. And today, you know that the manufacturing industry is going through a big change, what is typically called the digitalization. And one very important part of this digitalization is the additive manufacturing, which is a totally new way of making materials. In this the field, the biggest need is for new materials, and this is due to that the developing of the machines has been the major driver in this additive manufacturing business. But the materials now comes as the next question: what materials can we do in these machines? And this is what the focus of VBN Components has been from the very beginning. And today we are the only company developing and producing hard and wear-resistant materials by additive manufacturing. And we have introduced the Vibenite as the wear-resistant material group. And this is what we are doing at the moment. If we look into our materials, we today have 6 different wear-resistant materials. If you look at this screen here, you have we can start from the bottom, which is the Vibenite 130. This is a new alloy that will be launched after the summer, and this is a tool steel, and it's the hardest range is about 48 to 60 Rockwells. So this is a very tough tool steel material. You can compare it to H13, which is the most common tool steel material in the world. After that, if you go up in hardness scale, we come to the Vibenite 150, which is a high-speed steel material with a lot of carbides in it, and also higher hardness. It's a metallic matrix with carbides. If we move even higher up, we come to the Vibenite 280 and the 290, and they are also high-speed steel materials. So to 150, 280, and 290, they are in the same high-speed steel region. So here you have the difference is the carbide content and the hardness. And the Vibenite 290 is the world's hardest commercially available steel materials. Very good. And these alloys are the higher speed steel alloys are very good for toolings typically, but it could of course be used in any kind of wear resistant demands. If we go to the Vibenite 350, here we have a combination of corrosion resistance and wear resistant. So that is the new thing in this. And then you have a hardness of about 60 Rockwell, and then you have carbides and nitrides in the material. After this, I will show you a number of examples for these materials where they can be used. And the top of the material range at the moment is the Vibenite 480, and this is the biggest world news we have. This is a hybrid carbide metal, and this is a cemented carbide type, but it is not cemented. This is why we call it the hybrid carbide metal, because hybrid is from the best of the high-speed steel material, which is the toughness, and then we take the best from the cemented carbide material, which is the hot hardness. And this is why you call it hybrid. And here you have an extreme amount of carbides and a hardness range of 66 Rockwell approximately. These are the alloys we have, and all these are patented. We have a high hardness, wear resistant, but also we have a high strength, and we have a high toughness in the toughest alloys, and we also in general get very, very good fatigue resistance due to the high cleanliness of the materials. That is one of the major things in our materials. It's only extreme properties in what we look at. If we look at benefits, and we have tried to divide them into 4 groups here. You can first look at the environmental friendliness of the materials. You get the good thing is that with this additive manufacturing technology, now it is possible to choose a better alloy for your end application. And that leads to the total sum of the material wasted will be much, much less, because you can have better material in your end tools. So here you can see, just to sum up, we have a 90% reduction of material consumption. We have a reduction of energy needed for producing the material and shaping the material. We also, of course, have less transports and much quicker development for better products. In addition, we have long experience in this field, so we can support you with good help when you are trying to develop something new to really use this technology at its best. The end performance is, of course, a very, very important part of this. And then we have the alloys, which I presented for you. But typically, we have very, very high wear resistance and very high hardness. And now you do not need to soft machine the materials. You only go for the final shaping, which is a form of grinding or EDM. You also have good possibilities to use the design, the additive manufacturing design possibilities. You can have full hardness. You can also, the materials are also totally pore-free, so that you can get a very, very good material all the way through in some different applications. One other important factor of this is the simplification in production. And this means that we deliver components in near net shape. So you don't need the difficult machining of very, very highly alloyed materials. And you don't need the stock of materials. You get much shorter delivery times, and you can, in many cases, you can also skip the coating needs, for example. If we compare the Vibenite alloys with other additive manufactured alloys, we can look at this graph, and this is from the European Powder Metallurgy Association. So we have added the Vibenite alloys into this, and here you can see on the lower hardness scale, you see all the existing additive manufacturing alloys, which is typically titanium alloys, super alloys, and so on. And in the higher region of typically the traditional additive manufacturing materials, you can see the more aging steels. And then you can see all the upper scale here, it's the Vibenite alloys all the way through. So today we are totally unique in this region, and this is also alloys which you can order from us tomorrow. So it's not a developing or a future alloy. This is things you can buy from us now. Why should you 3D print wear-resistant metals? This is a typical comparison. Today, when you produce a component, you first need a material which is made in a steel plant. And you know all the steps in the steel plant. This is 200 years of development, which have come up to a very, very good quality level. But still, it's extremely many process steps. Then you send the bar to some kind of warehouse, a bar stock, and then you cut it up, and then you go for the machining in your machining shop. And in the machining shop, you need to remove all the material which you produced in the steel part, almost. So you can see that this is extreme amount of process steps, and this is the big drawback with existing traditional manufacturing technique. By doing the Vibenite way, we take powder, and then we do the additive manufacturing printing, and then we heat treat them, and then we grind them, and then you have a finished component. And this is the major paradigm shift which we are presenting here. This is a totally new way of making components. If we look at cemented carbides, I'm trying to down here. I don't know why it's not popping. I try to switch slide. Here we go to the cemented carbide. Here we can look at the traditional way of manufacturing. You take your powders, you do a lot of process technology, and then you have to press a green body, which you need to sinter, and then you grind it. And then you have the demands and limitations of this. You have this large serious problem. You need the pressing tools. You know that it is a shrinkage and size, etc., etc. All this traditionally technology with a cemented carbide leads to very good material, but you have a lot of limitations. And typically you have a problem in the brittleness of the material, and you also have a problem in the complex. It's difficult to have a complex shape when you need pressing tools and green bodies and sintering. And also you need the large series. It's very difficult to make 1 or 2 or 10 of something when you need to do thousands of them to get the good in the long run. We do like this. We take the powder, we have the additive manufacturing, we heat treat it, and then we grind it. And then we have a finished component in Vibenite 480. So if you see this overflow of material technology to the new, then you see that it is an extreme big change in what you can do. If we look at the possibilities, just to sum up, the best profitability is achieved when you have explicit demands of wear resistance, hardness, heat resistant, or fatigue resistance. This is our alloys are performing the best. We also need some kind of size of the component today, and that is due to the rough surface. We still make component blanks with a rough surface, so you need to grind if you have a cutting edge or so on. And this is just a rule of thumb recommendation. 20 millimeters is not an exact value. It's just by the rule of thumb. It depends on your grinding cost, so that you can compare to the printing. You can also design components without the need for post-processing, so that you leave some surface with a rough surface that you can use. And you also need some kind of complexity. Of course, we can produce cubes or cylinders directly, but if we do that, then you do not use the additive manufacturing technology, the freedom you have. Of course, we can do a test cube, which you typically do also. But really, to benefit of this technology, you need the complexity. And you need to use that complexity for a better performance in your end application. Today, we have a limitation in detail volume, which is typically about 230 times 230 times 350 millimeters. And this is a machine parameter, what we have today. And the price, of course, it's set by a serial size. If we look at surfaces, I mentioned that we have rough surface, and we have, so you can see here on the picture to the left, you can see we have 3 types of surface. We have the upper melt surface, we have the side surface, that is the most typical, the largest area is the side surface of the component. And then you have number 3, which is a lower surface with support structure traces. And you can, to sum up, you can do a lot of things to really minimize the need of the support structure. But typically you need support structure to get good geometrical correctness of your component. If you don't, you get some swelling. We do not have the enormous problem as you typically have in laser printing, but since we are using the electron beam printing, but we have still the need of removing energy from, so that the component will stay into shape. Example 1. I will now go through a number of example areas where you can use this technology. It is, for example, power skiving cutters. And in this case, you can use better material than you use today. And you can also, as an example here, you can see in the middle here, we can add media channel, or could be for cutting fluid, or it could be for high pressurized air to remove chips or something. So this is a blank. This is a Vibenite 480 blank for a shaper cutter. Just an example of what you can do. So here you can use the technology in a good way. This is a very good area, which we are working a lot of at the moment. Then we have large gear cutting hobs. We have been in this area for a long time, and we see that the biggest benefit we can get is when you produce large hobs, where you need to reduce the weight and you need to use the best materials to get high cutting speeds and high cutting depths, so that you can get a benefit of this, the new technology in this case. And you can do a lot of things with this. And for example, here also you can add media channels to cool and to remove chips. Another area is pressure die casting tool. Here you have an example, which is a governmentally funded project we ran for a couple of years ago. This is aluminium casting, and we added a very coarse channel through this center of this material, of this tools. And this led to a reduction of temperature from 296 degrees to 185. And this is a very heavy reduction of hotspot temperature, which is very good for the lifetime of the tool. This is just an example of what you can do. They can be, of course, be smaller and bigger and so on. This is an example that it really works in the real world. Another in the same region, you can say, it's the plastic or metal forming tools or hot stamping tools. Also here you can use the technology to reduce weight, but you can also reduce the technology to have cooling channels or conformal cooling. You get longer lifetime with better alloys, but you can also reduce weight and reduce hotspot temperatures and so on. So we get a quicker tool changing time, and you get longer lifetime in your tools. Production tools, also a very wide area of what you can do. And here we show you some examples. Here in this case, I make a sample holder. It's very simple to take a drawing of a component you have, and then we invert it to become a holder. And the inversion, can you see here? You have this diamond, which we have shown you now, the public relations, and then we have done a holder to be able to grind this one. This is a very simple thing to do. And in addition, you can also use this rough surface to get a better grip in your chuck yaw, for example. So here you can use this technology in many different ways. So here's also a big area of to use this technology in a good way. Cutting knives, it's also an enormous area. Here you have sheet stamping examples, and here you have just very good knives in Vibenite T50. One example here to the left, you can see the sheet stamping here. That is that you can get a more uniform hardening by having the hole inside the tool, because it's the edge here that does the work, cutting sheet metal. But by having this hole, which is no cost at all in the process, then you can have much more easy hardening, so that you get a more uniform hardening in the process, and then you get the same hardness even if you regrind the tool. This is also just an example of what's possible to do. Wear protection is also a big area. It could also be anything. Here we have just an example of an elbow for a pipe, so that you can have a corrosive protection wear. But the new thing here is that you can shape very, very hard materials in complex shapes very easily. That is a new thing, and this you can use for wear protection. Other applications, of course, there are a number of possible things. Everybody needs something that has a wear resistance. But here we have, just to show you an example of Vibenite combo, is when we printed the Vibenite 290 upon Vibenite 150 to combine the toughness with the hardness. This is just an example of what you can do. We are asking our customers to come with the ideas just to show what's possible to do. This is our customer offer. Typically, we start with a pre-study. Customer asks us, is it possible to print this, or what material is the most beneficial? So we do a pre-study. It's a very simple thing. It always includes one print of a final tool. It can also include geometrical and drawing discussions, so that you get a help to draw your component into good shape, and then we pick the material which can work in the application. And the results is just the answer on the question, does it work technically? We can also go to the next step, and that is we can help you with a better analysis of your existing problem. Since we're good at wear and so on, we can look into your existing tools or components and see if we can help you with a better choice of material. And this is also the result, does it work technically? And then we have a pre-study which we call AM Utilize, and that is to use the additive manufacturing technology. Then we can have a discussion with you, our customer, what your demands are in the end application, and then we can together come up with a good solution, which is possible to print, but also which is the best thing to print. So that is a good thing to do. Then we have what we call production development project, and this is when you are interested in knowing how much can the cost be in large serial production. Then we have to do a number of test builds with many components to see how we can optimize the process. Then we have the direct print, which is a simple thing. You send us a drawing, you say what material you are asking for and what hardness you need, and then we do it directly. Or we do the small serial production. You have done the direct print, maybe I've done a pre-study also, so you continue to buy from us. If you don't want to have your own production and you're not interested in that, we can do the production for you. And then for the big serial production, then we can offer you a license solution, which we help you with choosing the correct machines, and we do all the printing, the pre-printing of component, and we come to you with your print line setup, and then we come with all the software for melting the powders correctly. And then you can also get the IP rights, and we can help you with the powder and so on. So this is the customer offer we get to you. And now we're into the question mark. That is my 20 minutes typically. So now I ask you for questions if you have some.
Yes, thank you very much, Ulrich. That was an interesting presentation. You showed us many interesting examples, and I agree with you 100% that new materials for additive manufacturing are the next big thing after having many different types of additive manufacturing machines available. And it's very interesting that you have such hard and wear-resistant materials available that will drive additive manufacturing to the next level, I think. So yeah, we have one question. There's another question. The first question is about selling. If you are selling these materials also, I read out the question. Do you use your own laser powder bed fusion process so you produce the components by yourself, or do you also sell the powder for other additive manufacturing machines?
Yes, it's a good question, of course. We are today using electron beam melting and for the thing we do today. And we are offering the total package of either you buy a component from us with all the melting, correct melting at site at our case, or we sell you a license solution where we say that which machine you should choose, and then we come with the settings. At the moment, this is not possible to just take the powder and use it in any machine. It's not that simple. And you also know that there are many, many different machines on the market. So of course, it's impossible to just sell a powder. In general, you can say that the material is two things. It's the composition of the elements, and it's the way you consolidate your composition. And the solidification is the melting parameters. So it's not possible to just buy a powder today. But of course, if someone is interested to develop this together with us, then it's possible.
Okay, thank you. That was a question from Frank Köhnen. And there are some other questions from Ismail Sadeghi from University West. He at first said, "Thank you, Ulrich, for the great presentation," and then started with question 1. Just wondering, how do you achieve the good surface finish on the parts? Do you do grinding or other surface finishing?
I can take that. The typical is that you grind the surface, and this is just because this is what you do today. But also, in addition, we are now working with a number of companies with new technologies where you can get better surface with some kind of post-processing techniques. So this is a developing area. But the most common today is that you grind a surface when you need the high finish.
Okay, he is continuing with question 2. How do you improve the internal surface quality?
This is the same thing. I believe you mean yes. That if you have a channel or something, then it's also possible to use some different kind of grinding technologies for channels. And this is also discussion with the customer what the demands are, because if you have a demand of if your demand is cooling, then it's very good to have a rough surface, because then you get a turbulent flow. But on the other hand, if you have a very rough channel inside, then you can get some residual dirt from your cooling media and so on. So this is a balance, of course. But there are already techniques now which you can pour grinding fluids through channels and so on. And this is just a discussion. Please ask us, and then we will do what we can together with the supplier.
Okay, thank you, Ulrich. He continues with question 3. Are you involved in new alloy development for improved wear and corrosion properties, or is it mainly on steels?
We are, of course, we have a number of secret material developing plans, but the Vibenite 350 is both a corrosive resistant and a wear resistant material. But I can see in general we are only looking into hard alloys that are difficult to machine. So we are not into I can say that directly, but we're not really interested in printing Inconels today. We don't have that. That is not our focus. We can do that, but we're not looking into that. So of course there are already a number of alloys with extreme corrosion resistant behavior, but we're not really looking into that today.
And there is a fourth question from Ismail. Which 3D printing techniques do you use?
We're using electron beam melting at the moment. But we are not bound to any technique. We just use what's best for the materials.
Okay, thank you. There is another question from Frank Koenen, I think. What will be the benefit of the new post-processing technologies? Cheaper or faster or better quality?
Well, you can say like this: if you have a cost today for grinding, and then you can come up with a simpler surface treatment technique, then you maybe can skip the grinding. Of course, not in cutting edges, because then you have an extreme tolerance and geometrical demands. But in general, and if we do that, then it will be much cheaper. Then you come much more closer to a final geometry directly, and so on. And we are of course working with printing as fine as possible, but it's, as you know, it's always a balance of printing quick and printing very, very fine. And typically you cannot have them both today, but in the future, cheaper and better quality.
Okay, thank you very much. That's also the same Ismail is saying again here in his last entry. Thank you very much again. It was very interesting. And we are already a bit over time, so we must close this now. I just want to say to the audience that you can find a participation certification in the webinar planning tool for download.
Yeah.
Yes, thank you, Ulrich. And yeah. Till next time, then.
As you said, if you have questions, of course you should contact me. Send me an email or give me a call.
There is another question arising. Maybe we should go through it also. You showed an example of hybrid component made of two Vibenite grades. Shall be possible to add Vibenite material in an existing plain part coming from conventional process?
And the simple answer is yes. We have already done that, and we are working on that. So it's just a question. Please ask us, and so we can continue with that. But we have already done that, because the printing machine we have is actually an excellent welding machine. So of course we can weld on top of other things.
Okay, that was a question of Christophe Reynaud. I think that was the last one.
Yeah.
Okay, then we are finished.
Yeah.
Thank you
again.
Thank
you very much.